All right. So part of arithmetic, part of what you'll be expected to do on test day is factoring. So a multiple of any number is any number that's divisible by the original value. So if you have a number like 2, a multiple of any number is any number that's divisible by the original value. So 2 is divisible by 2. 4 is divisible by 2. 6 is divisible by 2. In fact, any even number is divisible by 2. And so these are all multiples of 2. This is 1 2, this is 2 2s, this is 3 2s. 100 is divisible by 2, this is 50 2s. So multiples are having more than one of the original number. One or more of the original number. It's important to remember that 2 is itself a multiple of 2. Another way to think about it is whatever your multiples are, let's just say you have your original number, which is x. The multiples of x are 1 times x, 2 times x, 3 times x, onward to infinity. Anything, any number times x is a multiple of x. Okay, so those are multiples. I just gave you some examples. Relationships to factors. Tricky. Okay, so factors are things that go in the opposite direction. So with multiples, you're taking a number and making it progressively bigger. Pretend those are numbers. Factors are the individual numbers you used to multiply together to get this bigger number. So, for example, the numbers that or the numbers that you could use to multiply together to get that bigger number. Let's pick a number like 12. So, factors of, so here we had 2, 4, 6, 8. These are all multiples of 2. A number like 12, 10, 12. So 12 has a number of factors. You can multiply 1 times 12 to get to 12. You can multiply 2 times 6. You could multiply 3 times 4. And furthermore, you could actually multiply 2 times 2 times 3, which is actually what each of these are. Actually, it's what all of them are. So you can even get it down to even smaller numbers and put an infinite number of 1s in there. Anyway, so they're all, so 1, 2, 3, 4, 6, and 12 are all factors of 12 because they're all things that can go into making 12. Whereas 12 is a multiple of 6, 4, 3, 2, and 1. See, so factors, multiples, it's the same idea going in respective directions. Factors, you're looking to go back to the building blocks. Multiples, you're building up from the building blocks to a bigger number. All right, factoring. So factoring is an important part of the GRE. It comes in many different contexts, both numeric and algebraic, and so let's talk about it. Good approaches to these questions. So these are different types of factoring that you'll be expected to know how to do basically on site. One is, what are the factors of 90? The approach to take when they just ask you for the factors without specifying what those factors need to be, like compared to prime factors over here, I'm just peeking ahead there so you know what I'm talking about. If they don't specify prime factors, we're looking for any numbers that you can multiply together to get 90. So you start by making a factor chart or a grid. So usually you start with the easiest factors you can think of, 1 and 90. And then you start going up from 1, and then, well, can 90 be divided by 2? Yeah, it can. Okay, so 2 times 45, right? Well, can it be divided by 3? Yeah, it can. So then that's 3 times 30. Does 4 go in there? No. Does 5? Yes. So 5 times 18. Does 6 go in there? No. Does 7? No. Okay, so obviously if you can't do that type of division in your head very quickly, you can just punch it into your calculator. But it does actually help to be fairly good with this type of arithmetic without having to use the calculator. The more things you have to put into your calculator as opposed to just being able to know them, the more the risk is of you hitting a wrong button and getting a wrong answer just by miskeying something. So don't rely over much on the calculator, I guess is the moral of the story. Anyway, to finish my lesson here on how you do one of these factor charts, 6 didn't work, 7 didn't work, 8 didn't work, 9 works, and it's 9 times 10. You know you are at the end when there are no numbers in between the two at the bottom of the chart. Like, had it been a number like 36, we'd get all the way down to just 6 and 6 on one side. You know you're at the end. So you'd have 1, 2, 3, 4, 5, 6. you can stop there because then you're just going to be switching the factors to the other way around. So then the next number that's divisible, or that's a factor of 90 would be 10, but then we're going 10 times 9. So we just switched. That's how you know when you're done. So you just stop here and say, okay, I have all the factors of 90. Woo! So, had they asked us, how many factors of 90 are even? Well, we'd say there's 2, 10, 18, 30, and 90. So there are 5 factors of 90 that are even. So that would be the context of a question like that. Or in a quantitative comparison, would be column A would be 6, and column B would be the number of factors of 90 that are even. So they'll make it more complicated than just outright asking you what the factors of something are, but not necessarily a lot more complicated. Anyway, that's factoring. You do a tree like this, and you don't have to break it down any further. This is to be contrasted with prime factorization. Prime factorization is the thing I was showing you before, breaking it down to the smallest possible building blocks entirely. Going all the way down to what are the series of prime numbers that you would have to multiply together to get to 90. So you do this a little bit differently. You don't do this kind of chart. You do a tree. So you do 90. Now, this one we started off with 1 and 90. That never helps, because 1 is not a prime number. We're trying to get all the prime numbers that make 90, so we want to start with the lowest prime number. Do you remember what the lowest prime number was? Waiting. Do you remember? It's 2, okay? So remember, our prime numbers are 2, 3, 5, 7, 11, no 9, right? Because 9 also has 3 as a factor. 11, 13. Odd numbers after 2, and it's not every odd number. So these prime numbers are the numbers that have only themselves and 1 as factors. So we start with always the lowest prime number that works, in this case 2. It doesn't actually matter if you start with the lowest one, that's just what I do. You can start with any 2. Let's just actually start with 9 times 10, because that works out too. So we say that 90 is 9 times 10. And neither of these is a prime number, so they each can be divided further. 9 is 3 times 3. Each of those are prime, so we stop. 10 is prime, or 10 isn't prime, we break it down, that's actually 5 times 2. But each of those are prime, so we stop. So that's our prime factorization of 90. 2 3s, 1 2, and 1 5. Note that had we picked different numbers other than 9 and 10, it still would have been okay. What if we had started with 2, like I said? This is 2 times 45. 2 is prime, 45 is not. 45 is 9 times 5. 5 is prime, but 9 is not. 9 breaks down to 3 and 3. So you get exactly the same numbers. The tree ends up a little bit more lopsided, but you don't get more points on the GRE for having a balanced tree like this, okay? Nobody sees the tree, they only see the correct answer that you get. So, whatever numbers you can think of that you can divide 90 by, except for 1 and 90, are fine for prime factorization. And you just keep breaking it down until you've got no more primes left. Or no more non-primes left, I guess. And all you have left are primes. I usually circle them because then I remember, then if I have to add them up, it makes my life easier.